Okay, I'm going to get started. Today's announcements are just reminders of stuff I put up last time. So the Chapter 15 saplings due Monday morning, and also the exam review is Sunday 2 to 4 p.m. in Math 100. And I do have the lecture capture set up now. Hopefully that'll all be good. I'm not sure if that's going to get posted on the same page as the normal lecture capture, but if not, I'll put a link to it on the course website. Okay, questions about that? Okay, cool. All right, so where we left off last time was we're starting to get into Chapter 16, and we spent a little while on nomenclature, and then we got into sort of the general idea of electrophilic aromatic substitution. So we covered one example out of that category. We looked at halogenation of aromatic rings. So EAS reactions. So halogenation. So today we're just going to run through a handful more of them, and then if we get time we'll start looking at what happens when you put them together. Okay, so I guess when we looked at naming, the nitro group was one thing that came up as pretty relevant to this chapter, and that's actually what we're going to be looking at today. First of all, is how to stick a nitro group on an aromatic ring. Okay. So, as a reminder, the three steps that all EAS reactions have in common: you make an electrophile, then the ring attacks the electrophile, and then you pull a proton off of the ring to get aromaticity back. All right, so making the electrophile is going to be a little bit more complicated here than it was in halogenation, but once we get that going, then it's going to be all the same steps. So, making the electrophile actually looks a ton like acid-catalyzed dehydration of an alcohol. All right, so what we're going to start with is H2so4 and HNO3, so sulfuric acid, and then if you remember that second one from Gen Chem, that's nitric acid. So we are going to show nitric acid here, and H2so4 is just around as like a convenient proton source, like it usually is. There's not a whole lot of long-lasting chemistry it does other than contributing a proton to whatever needs it. Okay, so this first step is going to look pretty much analogous to when we did acid-catalyzed hydration of alcohols. It's actually going to be the lone pair from the OH comes down, takes a proton from the proton source. Just like if we're protonating an alcohol group, we need to turn this into a good leaving group if we want to get rid of an H2O molecule. Okay, and you're looking at this, and you're probably like, what the heck, why did we stick a proton on the left side on that oxygen instead of on the bottom right where it's got a negative charge and it's a better base? The answer is probably the majority of the time this would actually be the fastest to pick up the proton. And so this would pick up a proton, and then from there you can't do anything productive, so it would just lose the proton again. So this is probably picking up and dropping a proton like, I don't know, hundreds or thousands of times before the one time where the wrong OH actually takes the proton, and then you can actually make progress through the mechanism towards something else. Okay, so we get to here, we've got an H2O group that's protonated, ready to leave, and that's actually exactly what happens. It drops off. If it did that by itself, like if this were just an alkyl group and we were doing this to an alcohol, it would leave a carbocation behind. We're not going to be able to do this because the nitrogen already has a positive charge. So while that's happening, the negative charge on the other oxygen kicks down to stabilize the nitrogen and keep it at the same charge it was before. So where that gets us is nitrogen has its double bond O still on it, and it now has a double bond to that other oxygen, and it still has the same positive charge that it has the entire time. Okay, so this thing, N plus with a couple double bond O's on it, is called the Nitronium Ion. And this is the electrophile that the ring is about to get involved in. So if you just remember, generate the electrophile looks like acid catalyzed dehydration, just there's a little bit more detail going on the rest of the molecule. That's kind of all you need to know for that part of the mechanism. And then from here, it's the same stuff that we covered last time. We've got our electrophile, and now we just need the ring to come in and start doing its thing. So the alkene goes, or the pi bond goes and attacks nitrogen. Either one of these NO pi bonds can break up. And as a reminder, even though I didn't show it in the previous step, you can if you want. Kind of the key thing breaking aromaticity here is that one of the carbons currently has 4 sigma bonds coming off of it. So if we want to get aromaticity back, we're going to have to pull one of the extra bonds off of this carbon, and that involves ripping a proton off. Okay, so we've got this nitrogen group, this nitro group on here now, and whatever other even vaguely base-like thing we have around can now come take a proton, so that can be H2so4 minus. What's most likely is it's going to be the H2O that we kicked out. So I'll just show that doing it. And then you reform the pi bond that way. So like that. Okay, so that's the mechanism for this. Overall, you're just going to write whatever aromatic ring. And then the 2 acids that we used, HNO3, H2so4, and you get a nitro group on the ring. Okay, so questions about that? Yeah?
Are we allowed to show that deprotonation as ambiguous deprotonation?
This last part?
Yeah.
Yeah, that seems reasonable. So, Yeah, I guess like if you want to be specific, just make sure it's something that's not completely unreasonable, but you can also leave it vague, and that's fine with me. So, Okay, other questions about that one? Yeah. So kind of the key point for wanting to restore aromaticity is every carbon around the ring has to have only one other bond to something outside. And so you just added something onto this carbon that already had an H, and so if you want aromaticity back, you better get down to having only one group off that carbon. So in other words, the carbon that just got the new group is the one that's going to have to lose its H as the last step. Okay. Okay. Other questions? Yeah. Right, yeah, so you can either write it as just NO2, like kind of the condensed formula, or you can draw it out explicitly with the bonds and charges and everything. Either one is correct, and you could show like the explicitly drawn out thing in the overall reaction too. If you're doing the mechanism, kind of what's going on within the nitro group is kind of important, so you should draw out the charges explicitly there though. Because otherwise you're going to have a hard time doing arrow pushing in between like parts of this thing that you've just lumped all together, so, if that makes sense. Okay, so other questions about that one? All right, cool. So if not, then we can move on to something that's very similar to this, and that is sulfonation. And this is right, so I kind of glossed over a lot of sulfur chemistry towards the end of OChem 1 in the interest of time. But this is basically going to look like whatever our rest of the molecule is. So like this. So basically think of this as being kind of like sulfuric acid, which is sulfur with 2 double bond O's and an OH hanging off either side. Just we're replacing one of the OH groups with whatever our rest of the molecule is. So we're basically putting like sort of sulfuric acid light as a functional group onto our molecule. Okay. So, reagents that we use for this are, there's a few different ways to write it. The old way was fuming sulfuric acid, which is the same thing as saying H2so4 and SO3, sulfur trioxide. If you look at the formula, SO3 is basically like the dehydrated version of sulfuric acid. So if you add a molecule of SO3 to H2O, you're going to get H2so4. So basically think of this as like we've concentrated this sulfuric acid so much that some of it's actually starting to break up into water and SO3. And then the SO3 sort of comes out as really noxious fumes out of the mixture that we've made. Okay, so this is fairly rugged, old school chemistry. Very reactive, not very tolerant of other functional groups on the molecule. But for now we're just doing this all to benzene, so whatever. Okay, so as it turns out, SO3 looks like this, and even though it doesn't have an official positive charge on the sulfur, all 3 of the oxygens on here are fairly strong delta minus, which means the central sulfur is quite a big delta positive charge on it. So we don't actually have to do anything to make an electrophile here. SO3, sulfur trioxide, is actually electrophilic enough that we can just go straight into the mechanism without actually making an electrophile in the first place. So that's actually what we're going to do. We're going to just go straight into the part where benzene gets involved. Okay, so pretty much same as up here. Pi bond goes and attacks sulfur. One of the double bond O's breaks over. And then, again, ambiguous deprotonation here I'm okay with. If you want to be specific, probably like H2so4 minus might be something around that could come in, take the proton. All right, so that regenerates aromaticity. But then we do actually have to do one other thing to this functional group, and that is to get it to be neutral, we got to stick a proton back onto there. So we can sort of use sulfuric acid as like our proton shuttle. It can protonate what we need it to, and its conjugate base can like deprotonate what we need it to. Okay, so that's how we get the sulfonic acid group onto there. Okay, One other option that you do have for writing this out is we know we need to stick a proton onto the O minus. We know we need to remove a proton from over here. I have seen some sources that actually show this intramolecularly, where the O minus just kind of whips around and rips the proton off of where it needs to be taken from. And that sort of takes care of both steps at once. Geometry-wise, I am not sure if that's realistic, but proton transfer is kind of poorly defined, so if you show it that way, I'm okay with that. Or you can just use H2so4 as like your proton shuttle. Okay, so overall for this one, we're just going to start with whatever aromatic ring, and then SO3, H2so4, and we'll get the sulfonic acid group on there. Okay, so hopefully you're like getting kind of familiar with the pattern of how the actual EAS part of the reactions work. Like it's all pretty much the same reaction, just with a few minor details maybe to do with proton transfer once we get the electrophile made or purchased or added to the reaction or whatever. Okay, cool. So those two are fairly harsh older school chemistry. The next two that we're going to do, the last two in this EAS category, are probably the most useful in terms of synthesis because those are where we actually start making carbon-carbon bonds. All right, so these two and the halogenation one are good to be aware of, but they are kind of not as super useful moving forward. Okay. So the next two we're going to look at were both discovered by the same two chemists, but they have slightly different names because they do slightly different things. So Friedel and Crafts were the two chemists, and they did one version of this reaction that's called alkylation. So kind of like the name is implying, we're sticking an alkyl group onto the ring. Okay, so there's a few different ways to generate an electrophilic alkyl group. Okay, given that electrophiles commonly have positive charges, it's not too surprising that what we're going to be making is a carbon with either a full positive charge or a strong partial positive charge. Okay, so the way that we're going to do this, we actually have several different options. Kind of the most common way is with having a chlorine on there and then throwing in a Lewis acid catalyst. And the mechanism for this is going to be pretty similar to halogenation. EAS style halogenation that we covered last time. Okay, so think of AlCl3 as a Lewis acid catalyst that's electron deficient, kind of like FeCl3 or FeBr3. We're going to get this reaction started by halogen here can go attack the catalyst. And that puts a negative charge on the aluminum, positive on halogen. Okay, so that's all exactly analogous to what we did last time with iron and chlorine or bromine. Whether it stays like that, the way the halogens did, kind of depends on the nature of the R group. And this is tying back into what we know about carbocation stability. So from here, I'm going to actually split it off like if R is secondary or tertiary, it's actually stable enough to sustain a carbocation, so it can just go ahead and kick the positive chlorine out of there entirely. So at this point, you just break that RCl bond, kick the electrons onto chlorine, give it its lone pair back. That gets you a carbocation, and then draw this up here, AlCl4 minus, and then the carbocation that we have, benzene can go attack. And then, just like always, you got to pull an H off to get aromaticity back. So like that. Okay, so if it's secondary or tertiary, we're going to be generating like the straight up carbocation out of this. So, not surprisingly, this comes with a whole lot of things to watch out for. Basically anything that involves carbocations, watch for rearrangements. Okay, so we'll cover some pitfalls of things going wrong there. But as kind of another option that I'll cover first, if R is primary or methyl, then it doesn't actually form the full carbocation. In this case, it's actually going to do exactly the same thing halogenation did. So rather than breaking off a carbocation here, the ring's just going to come straight in, attack on R, and kick out the halogen at the same time. And then you're still generating the same byproduct, and you still need to get rid of an H to get your final product. Okay. So, questions about those two? Okay, so let's look at things going wrong and carbocation rearrangements happening. So if we try doing this reaction, okay, so this R group that I chose, you're probably already suspecting that it's pretty rearrangement prone because the halogen is attached one away from a heavily branching thing. So as soon as we kick that off of there, we get this secondary carbocation, which then, of course, is immediately going to do a shift to this thing. So by the time benzene comes along and gets involved, or whatever aromatic ring gets involved, and I won't draw out the whole rest of the mechanism, but the final product that you get is going to be this instead of what we were expecting to stick on. Okay, so the weird and surprising and unsettling part of this reaction is that even if we don't officially go through a full carbocation, like if we're doing primary or methyl, it turns out we can still get carbocation-like rearrangements going on. So even if no full carbocation forms, so say we're doing a primary like this, okay, so we're thinking, all right, at this point, aromatic ring's going to come along. It'll kick out the chlorine. We'll just form a bond from the benzene onto this end carbon. Turns out not quite, because this is a good enough leaving group, as it turns out, that this is actually going to rearrange faster than the aromatic ring can get involved too. So even though you don't officially have a full carbocation out here, it's going to act like it does because it's getting pretty close to a full charge on there. And just do a hydride shift onto that carbon and boot out the leaving group. So whether you go full carbocation or not, it's still going to rearrange on you. And then from there, you're going to get that alkyl group stuck on. Okay, so this is of somewhat limited utility. If you're trying to make an aromatic ring with a long N-alkyl chain stuck to it, this is not going to give you what you want because it's just going to give you some branching alkyl group instead if there's any possibility of rearrangement happening. Okay. So overall, I'll put up here. Aromatic ring and alkyl chloride and aluminum trichloride. And that gets you an R group there. Okay. One question that a couple people asked is, so this is an Lewis acid catalyst. FeBr3 and FeCl3 are also Lewis acid catalysts. Can we mix and match? Could we do this one with FeCl3? Could we do halogenation with AlCl3? Turns out, yes, it just tends not to work quite as well, I think. So I think these particular catalysts are the best choice for doing this particular reaction. But I think there might be a few examples that pop up, in the textbook or online, where people are using a different one here and there. And that also is good enough on paper. Okay, so questions about that one? Yeah?
Could you do RCl and then the FeBr3?
Yeah, so I think it, for some reason, it is not as great a yield as this way, but yeah, that would also work too. So, Okay, so one other kind of side note to this reaction is, so we're making a carbocation or something like it. Turns out that any of the other reactions we've seen in the past for making carbocations will also let us drop into Friedel-Crafts chemistry. So So for example, one of the very first reactions we ever saw, if you take an alkene and you react it with, in OChem 1 we did water and H2so4. If we do this without the water, so we're not giving this the option of doing an acid catalyzed hydration, we're just giving it the acid, we know that Markovnikov's rule says the carbocation is going to form there. That can actually be something that an aromatic ring can react with too. Okay, so this will let us stick on an alkyl group like that. So that's one option of doing it, kind of an older school way. Another option is acid catalyzed dehydration looking mechanism, where if we have sulfuric acid around, we can turn this into a leaving group. That can drop off, give us a carbocation here, and if we happen to have an aromatic ring around while this is going on, that can actually come attack the electrophile, the carbocation, that way. And we can get the same product out of it. So basically, like any way of making a carbocation, if you happen to have an aromatic ring present when the carbocation forms, then you could end up going into an EAS pathway like this. And it also helps if you limit the other options available to this molecule, like by not having anything else around really that can attack onto this carbocation, like the water we would normally use for hydration of an alkene. That kind of cuts down on this thing's options and makes it more likely that aromatic rings are going to come in and finish it up. Okay. So questions about any of those ones for Friedel-Crafts alkylation? Yeah.
Is the difference between the secondary, tertiary, and the primary just that in the primary example, the R's attack the same time that the chlorine gets electrons?
Exactly, yes. So it's almost kind of analogous to like SN1 versus SN2. Like for primary or methyl, it's a little bit more SN2 looking, where like the attack happens and the leaving group gets kicked out at the same time. And then like secondary or tertiary, it's a little bit more like SN1, where the leaving group leaves and then later on something else comes in. And it just comes down to like how stable is the carbocation in the meantime on its own? Like can it carry a charge for a while after the group leaves? So yeah. Okay. All right, so this reaction, kind of cool, kind of useful for forming carbon-carbon bonds, so long as you're not too picky about exactly what the R group looks like. But if you are going for a specific R group that happens to be like primary at the point of attachment, this is not going to be a whole lot of help to you, unfortunately. So the last reaction that we're going to cover from EAS is sort of the improved version of this, which is Friedel-Crafts Acylation. Okay, so an acyl group is about the same as an alkyl group, only at the point of attachment it's got a carbonyl instead of just a regular alkyl carbon. So we're going to set this up pretty analogously to what we did over here, only instead of just an R going straight into a chlorine, we've got the carbonyl at the point of attachment here, CO double bond. And so we're going to start out looking exactly the same. All right, so here's where things start looking different. If we were doing this with Friedel-Crafts alkylation, you would probably kick out the chlorine and you just have a carbocation. The big difference is we've got a lone pair having thing one atom away. And so that can actually, as you boot out the leaving group, rather than forming a positive charge on here, you can kick down the lone pairs on the oxygen here and avoid ever having to form a carbocation at all. All right, so I'm going to show it in the same orientation that I did before, but really this is a triple bond. It should be linear geometry around the carbon. So maybe I'll move that R group down. Okay, that looks better. Okay, so what we're making here is called it's an acyl group, but with a positive charge. A lot of the time, the way of indicating a positive charge in the name is IUM on the end, so like ammonium versus ammonia. So this is called the Acilium Ion. And that positive charge is not going anywhere because it has no reason to. If you put a positive charge on oxygen here, it's got a full octet on everything. It's much more stable than any carbocation you can make. So it's kind of locked in place onto the end carbon, conveniently. Okay, and then from here, it's going to be same old, same old. Ring gets involved. That breaks up. I guess based on where I drew the double bonds in that ring, I'm just going to show locations here, but it's like that. And then, like always, to reform the aromatic ring, we just got to get a proton off of the carbon that we added something to. Okay, so that gets us an acyl group onto the ring like that. Okay, so this, as it turns out, is a little bit more useful for doing long alkyl chains with no branching. Maybe I'll do a specific example for the overall reaction here instead of keeping it general. But if you have an aromatic ring, we could do, say, maybe this molecule, an AlCl3, and that would stick on, for example, that entire acyl group onto the molecule. Okay, so we're not going to cover it yet. It's in the chapter on carbonyl chemistry, or chapters on carbonyl chemistry. But it turns out later on we'll see a couple of reactions that will actually take a carbonyl and replace it with a couple of hydrogens instead. So this is actually a workaround to the drawbacks of Friedel-Crafts Acylation. This is pretty much the only way to get an N-alkyl chain onto the molecule is if we stick an acyl group on there, we can snip off that carbonyl and turn it into an N-alkyl group. Which is not accessible through regular alkylation. Okay. So this part you can't test on yet because you haven't actually covered those reactions, but that's kind of why acylation is cool and useful. Also, it turns out you don't need such harsh conditions because you're not making such a high energy electrophile. You're not doing a full-on carbocation. You're just making this acylum. So it's relatively easy to do. And actually, the reaction you're going to do in lab next week involves making an Acilium ion. Okay. One other drawback, or I guess one drawback to this reaction is doesn't work if the R group on the carbonyl is a hydrogen. So if you try doing it with this acid chloride, it turns out it's actually going to break down to, I think, carbon monoxide and HCl. So you actually need special reagents to make that happen. It's a separate reaction called Gatterman-Cook formylation, because this is a 4-mil group that we're not gonna bother getting into. Okay, so questions about that? Yeah.
Why would you use the other drilled class?
So it kind of depends, because we haven't covered, I guess, like how to get rid of carbonyls yet. Basically, if you want a carbonyl at the point of attachment, use acylation. If you want just an alkyl group, use alkylation, with the limitation that you may not be able to stick on the specific alkyl group that you want. And so in that case, you might have to resort to other carbon-carbon bond forming methods, like maybe the alkyl group is something where you could turn it into an epoxide and turn the ring into a cuprate and have them stick together that way. So this is a way of doing things, but you may have to resort to like something totally different if you want to form like the specific alkyl group you want. So, okay. Alrighty, so in the last 5 minutes or so, we're going to start looking at what happens if you're doing this to not just regular benzene. Okay. So what if the ring already has substituents on it? Because if we've got one substituent and we're adding another, we could end up with groups that are ortho or meta or para to each other. So the biggest thing to keep in mind here is the group that's on the ring first at the start of the reaction gets to determine the regiochemical outcome. Okay, and really it comes down to what is it doing to the carbocation that you make on the ring while the reaction is happening? During the one step where you've lost aromaticity, like how good or bad is that carbocation going to be? Okay, so we're going to split the groups that could be on the ring to begin with into 3 different categories. Okay, cool. So 3 categories of groups. So we're going to be looking at regiochemistry, and we're also going to be looking at how fast or slow is the reaction compared to just benzene. So this one is going to be activating, so the reaction goes faster, and ortho-para directing. Okay, so in general, these are going to be any electron donating groups, or I guess most except for the one weird third category that we're going to see. Okay, so anything with a lone pair on the atom attached to the ring. Okay, so like OH, OR, nitrogen with whatever on it. And the big exception here is halogens. Those are their own thing. That's the third category we're going to cover. Or things that are electron donating in a more subtle kind of way, which is electron donating through hyperconjugation. So R groups, in other words. So just straight up, alkyls are slightly electron donating. They just don't have a lone pair to do it with. Okay. All right, so let me just start in on the next category in like the minute that I have left. Well, actually, no. That's probably a good place to wrap it up. All right, so I'll finish this up on Monday, but I'll see you guys at the exam review on Sunday afternoon if you can make it.